Okay, so now that we know a little bit about how radioisotopes release energy so that their nucleus goes from a less stable state into a more stable state, let's take a look at equations that essentially represent these different types of decays. And along with that, we're also going to talk about ways that radioactive isotopes can be made, or we will talk about in a sense that radioactive isotopes can be made from essentially a non-radioactive isotope. Essentially, the processes of the decays, alpha decay, beta decay, positron emission, even releasing gamma rays, and what we'll talk about is transmutation, which is the non-radioactive isotope into the radioactive isotope. They are essentially examples of nuclear reactions. And what we'll talk about now, of course, are the way that they are expressed, which are what are known as nuclear equations. Okay, so nuclear reactions, just like chemical reactions, can be expressed by chemical equations. Nuclear reactions can be expressed by nuclear equations. Now, the biggest difference here is that, and we mentioned this earlier on in the videos itself, is that in a chemical equation, atoms cannot be gained, lost, or changed into atoms of other elements. As we saw with alpha decays, beta decays, positron emission, and such like that, you're having a change in the number of protons in the nucleus of that atom. And therefore, the identity of that element is going to change. So the ideas of balancing nuclear equations are different than what we saw for chemical equations. When we talked about chemical equations, all we had to do was add coefficients in front of the chemical formulas of the different elements or compounds that were present, so that for each element, you had the same number of atoms on both the reactants and the product side, taking each element individually. That really can't be the case here, because in most nuclear equations, the elements are changing their identities by releasing these different forms of radiation. Or, as we'll see towards the end, when you're taking a non-radioactive isotope and making it into a radioactive isotope, the identity is changing as well. So in a balanced nuclear equation, the sum of the mass numbers are equal for the reactants and the products, and the sum of the atomic numbers are equal for the reactants and the products. So we have to make sure two things are true. On the reactant side and the product side, we have to make sure that the sum of the mass numbers add up to be the same. And then second, on both the reactant side and the product side, we have to make sure that the sum of the atomic numbers add up to be the same. Now, those two sums are not going to be equal to each other. If they were, it'd be just a slim chance, but we're sort of looking at them separately. But both of those facts have to be true in order for a nuclear equation to be balanced. And as you'll see in a moment, in these nuclear equations, we're going to be using the atomic symbols for the elements, for the isotopes, in order to include both atomic number and mass number. Okay, so let's start with alpha decay. So what is known as an alpha emitter decays by releasing alpha particles. So when a radioactive nucleus emits an alpha particle, okay, so this type of substance would essentially be an alpha emitter. A new nucleus forms with a mass number that is decreased by 4 and an atomic number that is decreased by 2. Because if you think about it, earlier we talked about what an alpha particle contains. An alpha particle contains 2 protons and 2 neutrons. So in theory, an alpha particle would have an atomic number of 2 and a mass number of 4. That's where the 4,2-He came into play. The new atom that's formed should have 2 less protons and 2 less neutrons. So its atomic number goes down by 2, but its mass number goes down by 4, because 2 protons and 2 neutrons gives us 4 for a mass number. So let's take a look at a couple of examples. So here's one. AT with, and I remember, sorry, I just don't remember the name for AT off the top of my head. AT with a mass number of 218 is an alpha emitter. It decays by releasing an alpha particle. In the first example here, we want to figure out what the identity of the mystery substance that it becomes is. That's where the question marks are. So how do we do that? And a periodic table here is absolutely necessary. Got to have a periodic table. So on the reactant side, we have an atomic number of 85. So on the product side, we have to figure out, okay, what plus 2 is going to give us 85? And therefore, for our mystery substance, we're going to have an atomic number of 83, because 83 plus 2 is going to give us 85. For the mass number on the reactant side, we have 218. So on the product side, we say to ourselves, okay, what plus 4 is 218? That would give us 214. Now, the final piece of the puzzle is, what is the chemical symbol for our mystery substance? And again, the number we want to solely rely on is we want to rely on the atomic number. Because the only element in the periodic table with an atomic number of 83 is bismuth. Now, if you look at the periodic table, they give the mass number for bismuth is 209. But remember, the number in the periodic table for the mass number is essentially the isotope that exists in the highest percentage. There's an isotope of bismuth that also exists with an atomic number, with a mass number of 214. So that's why when we're looking to identify our elements here, our mystery elements, we have to solely rely on the atomic number. Now, if you're looking to identify a particle, which we'll see a little bit of as well, that's a little bit of a different ballgame. But when you're looking to identify a mystery element, you have to rely on the atomic number. And in this case, you recognize that you're looking for an element because you have to recognize that 42He is the chemical symbol, what we use, an atomic symbol, of what we use for an alpha particle. Let's take a look at the second example on the slide. So here we want to figure out what undergoes alpha decay to give us TL with a mass number of 207 and an alpha particle. So what would be the atomic number of our mystery substance? Well, 81 plus 2 is going to give us 83. So again, I didn't realize when I did this, but okay. Once again, our mystery substance is going to have an atomic number of 83. Mass number, 207 plus 4 is 211. And again, we'll identify the element based on the atomic number. The only element with an atomic number of 83 is, again, bismuth. But notice that this is a different isotope of bismuth than what we found in the previous example. Here we're using bismuth with a mass number of 211, or we found bismuth with a mass number of 211. Here we found bismuth with a mass number of 214. Isotopes have the same atomic number, but different mass numbers. Beta decay. So a beta particle is an electron emitted from the nucleus when a neutron in the nucleus breaks down to form a proton and a beta particle, increasing the atomic number by 1. So when a beta particle is released, it turns out that the mass number is going to stay exactly the same for the element. Okay. And the reason why that works out that way in a sense is because you're breaking down a neutron. So it'd be 1 less, but you're forming a proton. So essentially the mass number goes down by 1, but then it goes back up by 1. So it stays the same. And if you look at the atomic symbol for an electron or a beta particle, it has a mass number of 0 as well. However, what's going to happen is, and this is a little bit tricky sometimes, is that the atomic number is actually going to go up by 1. Because essentially your number of protons is essentially increasing by 1 in a sense. And the way we reflect that is in terms of the beta particle, the high electron, having a -1 atomic number. So it sort of works itself in a correct fashion, with the mass number and the atomic number for the alpha particle or the beta particle in terms of what happens when a beta particle is produced. Neutron changing down to form a proton. So inside that nucleus, the neutron goes down by 1, the proton goes up by 1. Mass number stays the same, but the atomic number increases by 1. And the way that the atomic symbol for the beta particle works out, it lends exactly to that. All right. So chromium with a mass number of 51 is a beta emitter. Okay. Substances isotopes that release beta particles are essentially beta emitters. What we want to do here is we want to find the mystery substance that it becomes when it releases a beta particle. Right. So let's start with the atomic numbers. On the reactant side, we have 24. So on the product side, what plus minus 1 gives us 24? And the answer here would be 25. 25 minus 1 is 24. Common mistake students make here is that they put 23. 23 minus 1 is not 24. 23 minus 1 is 22. 25 minus 1 is 24. Okay. Mass number of 51 on the reactant side. On the product side, what plus 0 is 51? Not a trick question. 51. Again, we're going to use the atomic number to determine the identity of our mystery substance. And the only element in the periodic table with an atomic number of 25 is manganese. Okay. Next example, now we want to figure out what the beta emitter was that released a beta particle and became fluorine with a mass number of 20. So on the product side, we have atomic numbers of 9 and -1. 9 minus 1 is 8. So on the reactant side, our mystery substance has to have an atomic number of 8. Mass number on the product side, 20 plus 0 is 20. I was about to say 20 plus 0 is 0. It's not. 20 plus 0 is 20. So now again, what would be the chemical symbol for our mystery substance? The only element in the periodic table with an atomic number of 8 is oxygen. So here, oxygen with an atomic number of 8 and a mass number of 20 would be the beta emitter in this example.